So in this lecture, we're going to introduce some new operations. So we studied about addition of vectors, multiplication of vectors. So now we're going to introduce some new operations. So first operation on vectors we'll introduce is the gradient operation. Okay, it's called the gradient operation. It's normally represented with the symbol del. Okay, it is represented with the symbol del. So del of a vector, let's take the vector to be A. Del of a vector is nothing but I. So we have to represent this as, and del is also actually a vector. Okay, so I d by dx of the x component. Okay, of the x component of A, and j d by dy of the y component of A, and k, the unit vector k, d by dz of the z component of A. Now, what this means is this is the multi-dimensional rate of change actually. So the resultant quantity, you can see, it will actually be a vector. Now, if I remove these two quantities and write just out the x component alone, let's just take the x component alone. Okay, let's just take the x component alone. What is this? This is nothing but the rate of change of this vector, right? So rate of change of, so I'll have only A, right? I'll have only, I can write just A. So this is the rate of change of the vector A, and we have, so this is nothing but the slope, right? The slope is the rate of change of the vector, right, with respect to the x coordinate. Now now the slope is just the magnitude number. So if I add a vector, that means I add a direction to the rate of change. Now I can generalize this and add more components, right? I can add j component, k component, and this is the gradient. So this is the multi-dimensional rate of change. Multi-dimensional rate of change. So this is about the gradient. The next, we'll introduce a quantity called the divergence. It's called the divergence. So what is this divergence? So this divergence is nothing but del dot A. Okay. So it's the dot product of two vectors. So the resultant will be a scalar. So the resultant will actually be a scalar. So what is del? Del is nothing but, this is only del. Okay, so del is nothing but this quantity is called del. So nothing but the unit vector and the time partial derivative of the respective component x, y, and z. So you multiply that with the a vector. Okay, you multiply with that with the a vector. A vector now will have what? A vector will now have ax and I, right? So and ay and j and az and k. So you multiply these two quantities. You take the dot product. When you take the dot product, the resulting, how, as I told you what the formula for the dot product is, you just multiply the coefficients of I. Okay, so this is ax and this is the operator d. So, so just take this dot product is nothing but the d by dx of ax plus d by dy of. So now you can see this is nothing but a scalar. This will be a scalar quantity. This will be a scalar quantity. So what is the physical meaning of this divergence? So we said that is the gradient is the multi-dimensional rate of change. This divergence is nothing but, we'll take an example. We'll take an example and we'll come back to this discussion. I'll just show you something. So it refers, divergence generally spoken about in where there is a flow involved. So if from a point, okay, if from a point, let's say, let's take a point here, let's talk about So from a point, there is a gain of flow outside. Okay, so we're talking about a field, flow field. Okay, this quantity A that we are talking about is the flow field, and if from that point that we are taking the divergence, if there is a flow outward, then the divergence is actually positive. Okay, the divergence is actually positive. That's what they've shown here. So from the point where the water is uh, pouring on this tank, the water is going outward. In that case, divergence is positive. Okay, divergence is positive. Next, we have, if you have a steady flow region, if you have a region like this and you compute the divergence will be 0. For this, this flow is represented by a vector field. So the direction, the magnitude of the flow is represented, and the direction of the flow is represented. That's why it's called a vector field. The flow is represented by a vector field. If you take the divergence of such a field, you will get 0. And if the flow is flowing inward, okay, the flow is flowing inward to a point, then you'll get a negative divergence. So that is what is shown here in this figure also. So you can see here at this point it's flowing into this hole, so the divergence is negative. So next quantity we'll talk about is the curl. So curl is nothing but this quantity, del cross A. So del is nothing but, I told you, this quantity. And how do you take a cross product? You take I, j, k, and the quantity d by dx, the quantity d by dy, the quantity d by dz, and then the vector components ax, ay, z. So you take the determinant and you get the curl. So this is the curl. So what is the physical meaning of this curl? So again, if this flow, the vector that we are talking about represents the flow, the vector field, the flow vector field of let's say wind. Okay, so it represents the magnitude, the vector that we are taking represents the magnitude of the flow and the direction of the flow. And this, if you take the curl of such a vector, it just represents how much the vector field, the flow is curling about a point. So here you can see this, here you have a cyclonic storm. So it curls about a point, it swirls about a point. So that will have a non-zero curl. That means it will have a positive curl. Okay, it will have a positive curl. And here, if the wind is flowing steadily, there the curl is 0. Okay, curl is 0. So that's about gradient, divergence, and curl.